There are many ways to begin, in earnest, our adventure into numbers and their arithmetic. On the one hand, a natural place from which to begin our journey is with one of the forefathers of the subject, Pythagoras, the celebrated ancient Greek lover of numbers from the 6th century BCE. On the other hand, it seems fitting to open with the great 19th century German mathematician Carl Friedrich Gauss, who has contributed either directly or indirectly to nearly every advance of every corner of number theory, and now is known as the Prince of Mathematics. Here we'll bridge the ages to study a common mathematical curiosity that each of these two prominent figures explored: the collection of figurate numbers known as triangular numbers. Triangular numbers can be defined intuitively as the number of billiard balls required to create larger and larger equilateral triangles. As we'll see, this basic idea leads to some very profound theorems about the natural numbers. In fact, this discussion will foreshadow our later discussion on searching for natural number solutions to certain equations, an area now known as Diophantine analysis. The triangular numbers have important implications both within our everyday world and the world of number theory. We'll see, for example, that the triangular numbers model the number of hands, one that would be shaken within any friendly encounter among a group of individuals. Generalizing these numbers will allow us to discover the central mathematical concept of arithmetic progressions. Arithmetic progressions are lists of numbers for which the difference between any two adjacent terms is always the same value. Both the even numbers, 2, 4, 6, 8, and so on, and even the odd numbers, 1, 3, 5, 7, and so forth, are examples of arithmetic progressions, because in each case, any two adjacent terms differ by 2. These arithmetic progressions of numbers are central and important objects within the study of numbers and will remain with us throughout our studies. Well, I want to open this lecture with a few words about the mathematical life of Carl Friedrich Gauss. Gauss was born on April 30th, 1777 in Germany. His father was a bricklayer and actually did not encourage his son to pursue advanced mathematics. However, from a very early age, it was clear that Gauss was a true mathematical child prodigy. And there are many wonderful stories about a very mathematically precocious young Gauss. One famous story, which, by the way, may or may not be true, but still remains a wonderful story, involves Gauss as a third-grade student and his teacher at the time, a J.G. Büttner. Büttner one day asked his students to add up the first 100 natural numbers, thinking that this would keep the class busy for some time. Perhaps Büttner didn't bother to actually prepare a lecture for the day. Who knows? Anyway, within a few minutes, Gauss approached the front of the class with a piece of paper in his hand. Gauss asserted that the answer to the sum was 5,050, which, by the way, is the correct answer. In the story, Büttner asks Gauss how he computed this sum of the first 100 numbers so quickly. And so Gauss describes his clever idea, which I want to share with you now. So what Gauss does is a lesson that we've seen in the previous lecture, which is to look at things from different points of view. So we take the sum, which let's just call it S to give it a name since we don't know its value yet. So S will equal 1 plus 2 plus 3 and so forth all the way out to plus 99 plus 100. And now Gauss does something quite ingenious. He writes that exact same sum again, but with the terms written in reverse order. So he writes S again as S equals 100 plus 99 plus 98 plus and so forth all the way down to plus 2 plus 1. And then he adds these two equalities. On the left-hand side, we see s plus s, which gives us 2s. And on the right-hand side, notice that the columns of numbers always sum to the same value. 1 plus 100 in the first column equals 101. 2 plus 99 equals 101. And all the way down to the penultimate one, 99 plus 2, which is 101, and even the last one, 100 plus 1 is 101. So we see 101 added to itself a whole bunch of times. And how many? Well, one for each natural number from 1 to 100. So therefore, we see 100 times 101. So Gauss produces a wonderful equation, which is that 2 times the sum, 2 times s, equals 100 multiplied by 101. And we can solve for s by itself by dividing both sides by the 2. And so we see s equals 100 times 101, all divided by 2, which equals 5,050. Wonderful. Well, in fact, Gauss's ingenious idea can be generalized. Let's find the sum of the first n natural numbers where we don't even know the actual precise value for n. We'll do this now in general. And we'll use exactly Gauss's ideas. We'll follow Gauss's footsteps, his young footsteps. Let s equal the sum of the first n natural numbers. So s equals 1 plus 2 plus 3, all the way out to n minus 1 plus the last one, n. Now we write the exact same sum again, but reverse the order of the summands. So s equals n plus n minus 1 plus and so forth, decreasing each time until we get down to plus 2 plus 1. When we add both of these together, we see s plus s is still 2s, and now each column adds to n plus 1. 1 plus n in the first column is n plus 1. 2 plus n minus 1 is n plus 1, and so forth, all the way down to the last term, n plus 1, which is n plus 1. How many n plus 1s are we adding together? One for each natural number from 1 to n. So there's n of them. And so we see n multiplied by n plus 1. If we divide both sides by 2, we come up with a beautiful formula. S equals n multiplied by n plus 1, all divided by 2. Therefore, Gauss discovered a very clever proof of this formula. 1 plus 2 plus 3, all the way out to plus n, equals n times n plus 1, all divided by 2. Well, this formula is really quite a work of beauty, and it actually transforms a seemingly intractable sum to a very manageable form, which we call a closed formula, a formula that has no dots in it, but just is totally compact. For example, if we want to find the sum of the first 1 million natural numbers, we now see that the answer is 1,000,001 multiplied by 500,000. Not bad for a third grader, don't you think? Pretty clever guy. Today, Gauss is considered one of the greatest mathematicians ever. Gauss's passion toward number theory was clear. In fact, he believed that basic relationships between numbers were fundamental in all matter, even beyond mathematics. He once wrote that God does arithmetic, and is credited with having said that mathematics is the queen of the sciences and number theory is the queen of mathematics. So you could really see Gauss's passion, not only for math in general, but number theory in particular. Later, Gauss was actually crowned the Prince of Mathematics by the mathematical community, and that is his moniker to this very day. Now, he was a perfectionist, and thus his accomplishments were much more numerous than his actual publications. In fact, one of his favorite mottos was the phrase, "few but ripe," meaning he wouldn't publish lots and lots of little results, but instead the results that he did publish were quite important and quite dramatic. Another favorite motto of Gauss's, by the way, comes from Shakespeare's King Lear, in which we see, "Thou nature art my goddess, to thy laws my services are bound." And so you can see Gauss's connection between nature, mathematics, and numbers. Gauss is so respected and admired that his image actually appeared on the 10 Deutschmark notes before the euro actually came into fashion. And so here you can actually see Gauss on real money. Not bad. Well, let's now return to the sum of the first n natural numbers, which we found equals n times n plus 1, all divided by 2. Now, this sum is called the nth triangular number. The first few triangular numbers, therefore, if we just plug in, we see 1, 3, 6, 10, 15, 21, and so forth. And we can see this by just computing. We have 1, that's just 1. The next one would be 1 plus 2, which would be 3, the next number on this list. 1 plus 2 plus 3 gives us 6. If we add 4, we get 10, and so forth. So we can see that these numbers are correct. Now, these numbers are called triangular because they represent the number of billiard balls that can be arranged into an equilateral triangle. Notice that the fourth triangular number, 10, equals the number of billiard balls used in a game of pool or the number of pins used in bowling. And by the way, notice that the Deutschmark that has Gauss's picture on it is a 10 Deutschmark. 10, triangular number. Coincidence? Who knows? Anyway, applying Gauss's third grade formula, we see that 5,050 balls are required to make a triangle having a base of 100 balls. And so an equilateral triangle that would be 100 here, 100 here, and 100 here would require 5,050 balls. Well, we can use the visual description of these numbers as triangles to actually give a geometric proof of Gauss's sum formula. And I want to share that with you right now. So if we take a look at the triangular number 10, which is the familiar number that we see if we play billiards or if we bowl, you can see that it forms an equilateral triangle. We have 4 plus 3 plus 2 plus 1, and that gives us the 10. Wonderful. Well, now I want us to rearrange this triangle a little bit. No longer have it be equilateral, but I'm going to create a right triangle by just slightly sliding over these balls. Now, I want you to notice something. This is almost like a magic trick. There's no sleight of hand. I'm never actually removing any of these billiard balls. But instead, I'm just rearranging them a little bit by sliding them over. And notice that in doing so, I actually create a right triangle, but the number hasn't changed. It's still the triangular number 10, and you can count and see. 4 by 4. But now this lends itself to actually some wonderful observations. Because to prove the formula of Gauss, I take another copy of this triangular number, and notice that, in fact, here I have another copy, which you can see is indeed also 4 by 4. You can count 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Great. So these are identical. But look what happens when I turn this around. Then the two fit together, and I form a rectangular figure. Do you see it? Amazing. Well, if I can now find the area of this, which is actually very easy to do, what's the area? It's 1, 2, 3, 4, multiplied by 1, 2, 3, 4, and then an extra 1 here, so it's 5. So it's 4 by 5, which, of course, is 20. So there's 20 dots here. But remember, I've overcounted because, in fact, I added a whole extra copy. So I actually have double the actual answer. So if I were to divide by 2, then what I would see would be 20 divided by 2, or 10. And that's exactly how many numbers we have, how many dots we have that are orange. So let's say this again. By taking an extra copy, so now I have 2 times the number of dots, turning them around and placing them in this configuration, I see a rectangle, and the rectangle's base is 4 plus 1, and the height is 4. So therefore, the area will be 4 times 4 plus 1. I divide by 2, and that gives us the number of dots here. Well, in fact, this geometric proof holds for any number of dots as long as they form a triangular number. Think about it. If this were n by n, then when I put in this extra copy, I would see n multiplied by n plus 1. And so I'd see n times n plus 1, but I overcounted. I doubled the answer, so I have to divide by 2, and when I divide by 2, I come up with the formula that we actually saw in Gauss's formula, n times n plus 1, all divided by 2. Well, in an attempt to find structure within these numbers, we consider the sums of 2 consecutive triangular numbers. Again, always searching for structure, always searching for a pattern. So let's take two consecutive numbers in this triangular sequence and add them together. So here are the first few. We have 1 plus 3, which equals 4. 3 plus 6 equals 9. 6 plus 10 equals 16. 10 plus 15 equals 25. 15 plus 21 equals 36. 21 plus 28 equals 49. Now we can't help but see a surprising pattern. The sums are perfect squares. 4, 2 squared, 9, 3 squared, 16, 4 squared, 25, 5 squared, and so on. Well, we can actually establish that this observation holds in general and is in fact a theorem. We can actually see why this result holds by returning to our visualization of these numbers as triangles. And let's first try to do that right now live and then actually see the actual proof. So here, this is the fourth triangular number. Now, what if I add to it the third triangular number, which by the way is 6? Well, I happen to have the third triangular number in its configuration right here. You can see it's 3. And if you add the dots up, we see 1, 2, 3, 4, 5, 6. And so that's right. So now what if we add these dots to these dots? Well, doing that like this doesn't seem to really reveal anything. But watch the magic when I turn this around and fit it in place. Isn't that amazing? Like magic, we form a perfect square. It's a 1, 2, 3, 4 by 1, 2, 3, 4. It's a 4 by 4 square. So the number of dots in the sum of the orange plus the white is a perfect square number. In this case, 16. Really, really neat. So now, that shows us that this makes some sense, but now we can actually see why this is true for real. So this result can also be proved using algebra. And so let's take a moment to think about this. If we add the nth triangular number to the n plus first triangular number, then what would we see? Now, we're going to do some algebra here, so let's just have some fun, relax. Well, the nth triangular number by Gauss's formula is n times n plus 1, all divided by 2. And now I'm going to add the next triangular number, which means that we have to add 1 to all those little n's. So I see n plus 1 times n plus 2, all divided by 2. That's the next triangular number. Well, what do we do here? Well, we just combine those two fractions, and so I see n times n plus 1 plus n plus 1 times n plus 2, all divided by 2. And if you notice, in the numerator, we have this common factor of n plus 1 in both the first term and the second term. And so I can actually factor that out. And when I factor it out, I'm left with n plus 1 times the quantity n plus 2. And that's all divided by 2. Well, what's n plus 2? That's 2n plus 2. So I see n plus 1 times 2n plus 2, all divided by 2. Well, notice that in the 2n plus 2 factor, I can actually factor out another number, namely 2. When I factor out that 2, I see 2 times n plus 1 multiplied by n plus 1 divided by 2. And the 2 divided by 2 actually cancel, and I'm left with n plus 1 times n plus 1, which is n plus 1 squared. This actually establishes the result in general, since I never said what n was. We see that whenever we add two consecutive triangular numbers, their sum will always be a perfect square. Well, on July 10th, 1796, at the age of just 19, Gauss proved that every natural number is the sum of at most 3 triangular numbers. Absolutely amazing. For example, if we take a look at the number 17, that equals 1 plus 6 plus 10, each of which we've seen is a triangular number. Even a number like 100 equals 45 plus 55, and you can check that both 45 and 55 are indeed triangular numbers. He stated this result in his diary as, Eureka! Num equals triangle plus triangle plus triangle. And he actually drew a little triangle plus triangle plus triangle. And he was really delighted to discover a proof of this really deep mathematical result. Now, in fact, Pierre de Fermat asserted that this result holds way back in 1638. Now, Fermat claimed to have a proof of this result, but no such proof has ever been found. And we'll talk about Fermat quite often in this course, and we'll see this is a recurring theme. Fermat states assertions and claims to have proofs, and often does not have a proof, or certainly the proof wouldn't be necessarily correct. Oh, I'm sorry, complete. It would be correct, but not necessarily complete. Well, establishing this result is extremely challenging, very difficult proposition indeed. Let's just think about what would be involved. Given a natural number, let's call it capital N, we would have to find whole numbers, so natural numbers are maybe 0, x, y, and z, that satisfies the Diophantine equation x times x plus 1 divided by 2, plus y times y plus 1 divided by 2, plus z times z plus 1 divided by 2 equals n. Now where did that come from? Well, think about it. Each one of those represents a triangular number. That's the formula for triangular numbers. So it's saying that one triangular number formed by the x's plus another triangular number formed by the y's plus the third triangular number formed by the z's has to equal the given number n. Now, if we actually multiplied everything through by 2, the denominators on the 2's would, on the left-hand side would go away, and we'd see a 2 on the right-hand side multiplying n. And if we distribute out all those multiplications, so there's no more parentheses, this would become the equivalent equation x squared plus y squared plus z squared plus x plus y plus z equals 2 times n. So we have to find whole number solutions, x, y, and z, that satisfy this very complicated equation for any natural number, capital N. Very tricky indeed. Although this issue does foreshadow our explorations into finding solutions to such equations later in our course. So we'll come back to this, although we won't solve this question since it really is genuinely difficult indeed. Well, I wanted to take a moment to consider an application in which these triangular numbers actually arise. Let's suppose that a group of people assemble for a meeting. Before the proceedings begin, each pair of people shakes hands exactly once. How many handshakes are there? Well, let's think about that. With 2 people, there's of course just one handshake, because there's 2 people, they shake hands with each other. With 3 people, we have that one handshake, but now this new person has to shake hands with the 2 previous people, and so we see now 2 more handshakes, so a total of 3 shakes. So now we have 3 handshakes. If we introduce a 4th person, that person has to shake hands with all 3 people, which means that now we have 6 handshakes. With 5 people, we would have 10 handshakes, and so forth. Well, we discover that the number of handshakes will be, in fact, a triangular number. Who would have guessed it? Something from number theory actually helps us count something. It's rare, but it's wonderful when it happens. While this application might seem a little bit frivolous, such counting issues have applications in networking. If n computers are to be directly connected with each other, then the number of connections would in fact exactly be the nth triangular number. Now, in fact, counting complex scenarios such as handshakes or computer networks is challenging. And that area of mathematics is known as combinatorics. And the handshake question is an example of what is known as combinatorial number theory. Well, let's now generalize the idea of triangular numbers in a slightly different direction. Recall that the triangular numbers arose from adding the numbers from a very simple progression, 1, 2, 3, 4, 5, and so on. What feature makes the progression of natural numbers so simple? Well, to generate the next number on our list, we merely add 1 to the previous number. Well, we can now generalize this feature. So we pull out this feature and see if we can extend it. Let's consider the progression that starts with 1, and to generate the next number, we add 2 to the previous number. This new progression is 1, 3, 5, 7, 9, 11, 13, and so forth. We've just produced the odd numbers. Well, progressions of numbers for which the next number in the list is produced by adding a fixed amount to the previous number are called arithmetic progressions. We're performing addition, arithmetic to progress the numbers. So the lists 1, 2, 3, 4, 5, and so forth, and even the odd numbers 1, 3, 5, 7, 9, and so forth, are both examples of arithmetic progressions, because in each case, there's a fixed number that I can add to one number to get the next one. In fact, the even numbers, 2, 4, 6, 8, 10, and so forth, also form an arithmetic progression. Because if I start with 2 and then continually add 2, that gives me 4, add 2 again gives me 6, add 2 again gives me 8, and we see this progression. Well, we can build any progression just by knowing the very first number together with the fixed amount to be added to create each successive number. For example, if we start with a 5 and add 3 each time, then we have the arithmetic progression 5. Now to get the next one, we have to add 3, so that gives us 8. Now we take 8 and we add 3 yet again to get 11, and so we see the arithmetic progression 5, 8, 11, 14, 17, 20, 23, 26, 29, and so forth. Well, we discovered the triangular numbers by adding up the first few numbers from the simple arithmetic progression 1, 2, 3, 4, 5, and so on. Recall that we found that the formula 1 plus 2 plus 3 plus 4 all the way out to plus n equals n times n plus 1 over 2. So one generalization of triangular numbers arises by considering the sums of the first few terms from any arithmetic progression. For example, if we return to the arithmetic progression we just saw, 5, 8, 11, 14, 17, and so forth, we keep adding 3 each time, then we can generate the list of sums of these numbers as we progressively add the next term. That list would begin 5, the first number, then 5 plus 8, which is 13, then 5 plus 8 plus 11, which is 24, and then 5 plus 8 plus 11 plus the next one, which is 14, which equals 38, and so forth. So our sequence of sums would be 5, 13, 24, 38, 55, and so forth, and would provide one type of generalization of the triangular numbers. Well, beyond extending the notion of triangular numbers, arithmetic progressions are one of the pillars of number theory and will prove to be extremely important in our future lectures. So while we've seen the wonderful world of arithmetic progressions, where we have this very, very simple pattern, and how in the very simple case where we just look at the arithmetic progression of the natural numbers themselves, we come to these wonderful triangular numbers, we will take the notion of arithmetic progression with us, and we'll actually see it as a recurring theme throughout our studies. For now, I want you to enjoy the triangular numbers, and not only the wonderful theorems that we discovered about the structure of these numbers, but perhaps more importantly, the beauty of the proofs, both geometric and algebraic, that proved the assertions were in fact a fact.